Welcome back to the series of lectures on ODE and its applications. Today we will discuss about the existence and the uniqueness of solution of initial value problems. You have already seen that in the theory of first order and second order differential equations, the need of existence and uniqueness of solution, and this session we deal with an initial value problem, that is a differential equation of the form dy by dx is equal to f of xy. So call this as a given differential equation where f is a function is defined on r cross r to r is a function not necessarily linear. So this model can handle both linear and nonlinear differential equations. Along with the differential equation, we also give an additional initial condition y at x0 is equal to y0. So call this as equation number 2. This equation 1 along with the initial condition 2 is known as an initial value problem, and equation 1 plus 2 this form an initial value problem. Is an initial value problem and commonly written as IVP, initial value problem. Now this model, this first order differential equation could be a model derived from a physical system, and a very important question once a model of this form is framed is, does there exist a solution to this equation? If the solution exists, will that solution be unique, and also will the solution varies continuously with respect to the initial condition y0. So these are the major 3 problems which we will discuss in details in this session. See, first let us see what do you mean by a solution of this differential equation. So solution of IVP. So equation 1 and 2 this form an IVP. The solution of IVP. The solution of IVP is a function say yx which is differentiable and satisfies the equation 1 and the initial condition 2. So a solution since the equation is dy by dx is equal to f of xy, So, we require that the solution y has to be a differentiable function. It has to satisfy the differential equation. So, therefore, it is a differentiable function and also satisfies a given initial condition y at x 0 is equal to y 0. In other words, we are looking for a function. So, we look for a function y x which is differentiable we look for a function y x which is differentiable and starts from the initial point x 0 y 0, starts from the initial point x 0 y 0, that is if this point is x 0 and this point is y 0, say this is a point x 0 y 0. We are looking for a function which starts from x 0 y 0 and whose slope slope of y x at any point slope of y x at any point x y in the x y plane is dy by dx at x y, which is given by the differential equation f of x y. So, therefore, the solution of a differential equation 1 with the initial condition 2 is a function that starts from the initial point x 0 y 0, of course. So, that is differentiable and the slope at any point is given by dy by dx is equal to f of x y, which is coming from the differential equation. F of x y is given to us. So, slope at any point x y is known to us and the initial point is known to us. We are looking for the function which starts from x 0 y 0, and whose slope is at any point is f of x y. Now, we deal with the well-posedness of this problem. Well-posedness of mathematical model. So, the mathematical model is given by the initial value problem. So, let the mathematical model is given by the differential equation dy by dx is equal to f of x y with initial condition y at x 0 is y 0. So, this model is well posed if the following three properties are satisfied. If the following three properties are satisfied. So, this well-posedness was raised by the famous French mathematician J. Hadamard. So, the well-posedness problem was introduced by Hadamard, and Hadamard raised the issue of well-posedness, which says that given a mathematical model, if the model satisfies the following three properties, then the model is well-posed. The first property is there exists a solution to the initial value problem. There exists a solution. So, that is a existence problem. So, which is known as a existence problem. So, given a mathematical model, the first question is to decide whether there exists a solution or not. That is the existence problem. And second problem is a solution unique? The solution is unique. So, that is uniqueness problem. Uniqueness problem. If the solution exists, will there be more than one solution, or the solution is unique? And the third problem or third property of a well-posed problem is the solution's behavior So, solutions behavior changes continuously with respect to the initial condition. So, these three problems, the first one is there exists a solution to the mathematical model. The second problem is whether the solution is unique, and third problem is whether the solution changes continuously with respect to the initial condition. Here it is y0. So, the third problem is known as the stability problem. So, the existence problem first, then the uniqueness problem, and the third one is the stability problem. So, if a model is not satisfying these three properties, so any model which is not satisfying these three properties is known as a ill-posed problem. Ill-posed problem. A problem does not satisfy the Hadamard well-posedness. Conditions. Now we will discuss the problem of existence, uniqueness and stability of some simple differential equation, simple initial value problems. So, let us take an example. So, example 1. So, consider the first order, consider the first order homogeneous linear differential equation, homogeneous linear differential equation given by dy by dx is equal to 2y along with an initial condition, say y at 0 is 3. You have already seen how to solve this linear differential equation in the previous lectures. If you separating out the variables and integrating, so separating out the variables and integrating we obtain dy by y is equal to 2 dx if we separate out the variables, and if we integrate adding a constant c, we get ln of y is equal to 2x plus c, and taking exponential on both sides we get y of x is equal to e to the power 2x plus c, which is equal to say the first constant is c 0, you get c into e to the power 2x, where c is equal to e to the power c 0. So, therefore, the solution of this differential equation, I have not applied the initial condition, the solution of this differential equation can be obtained easily by separating out the variables or by the method of separation of variables. So, yx is equal to c e to the power 2x, which is a family of solutions or curves. So, one parameter c, for this is a solution for every value of c. So, c is an arbitrary constant. So, the given linear differential equation has got infinitely many solutions, and for every c the given expression y this y is equal to c into e to the power 2x is a solution. So, if we plot the solution, this is one solution or one value of c. So, this is c1 e to the power 2x, and this could be another solution for c2 e to the power 2x, and you have a family of one parameter family of solutions. So, these are all solutions, a family of solutions to the given linear differential equation, and this solution is known as a general solution. So, yx is equal to c e to the power 2x is known as a general solution. to the differential equation dy by dx is equal to 2y. So, I have not applied the given initial condition. So, once I give an initial condition, so applying the initial condition, y at 0 is 3, then this becomes y at 0 is equal to 3, which is equal to, we can plug in the value of value to x as 0. So, c into e to the power 2 into 0, so which is c, or in other words c is equal to 3. So, therefore, we get the solution yx is equal to 3 e to the power 2x. So, this is a solution of the given differential equation satisfying the given initial condition. Say if this point is 3, say then 3 e to the power 2x. So, this is a solution if this point is 3. And for a particular value of c, the general solution becomes a particular solution, and if you give a specific value to the arbitrary constant c, then the solution we obtain is known as a particular solution. A particular solution so y of x is equal to 3 e to the power 2x is a particular solution, and similarly y of x is equal to 5 e to the power 2x. They are all particular solutions okay, by putting various values. So, initially it is c is equal to 3, and second case c is equal to 5. So, a particular solution is obtained by giving a particular value to the general solution. Now, for a given differential equation, there can be another type of solution which is known as a singular solution. So, three types of solutions we have discussed. One is a general solution, and a particular solution, and a third type of solution is singular solution. So, general solution we obtained, and in the general solution there is a parameter that is a parameter family of solution. So, in our case it was y is equal to c e to the power 2x, and particular solution, say c is equal to, you particularize the value of c is equal to 10, then y is equal to 10 e to the power 2x is a particular solution, and a singular solution is a solution which cannot be obtained from the general solution. But in the previous example we have only these two types of solution, general solution and a particular solution, and singular solution does not exist for the previous example. Now, we consider an example. So, example say call it 2. So, consider the nonlinear differential equation say dy by dx is equal to y minus 3 the whole square. So, we have seen that this equation is obviously a nonlinear differential equation. So, how to solve it? By the method of separation of variables. By the method of separation of variables, separating out the variables and integrating, you get this is dy y minus 3 square dy is equal to dx, and integrating plus adding a constant c. So, integral of 1 by y minus 3 the whole square is minus 1 by y minus 3, which is equal to x plus c. So, this simplifying, we get y is equal to, you take y minus 3 over there and minus 1 by x plus 3 there. So, y is equal to 3 minus 1 by x plus c. So, this is a general solution for every value of c. Every value of c, this is a solution. So, therefore, this is a general solution. So, this is a general solution, and if you give particular values to c, say for example y is equal to 3 minus 1 by x is a particular solution. So, where c is equal to 0, okay. When c is equal to 0, you get a particular solution. So, this is a particular solution. Now, you can verify easily that y is equal to 3. Once you substitute y is equal to 3, it is a constant function, into this equation, and this equation is satisfied. Is also a solution, is also a solution, but that is not obtained from the general solution, and therefore, this is a singular solution. So, y is equal to 3 is a singular solution, is a singular solution. So, this example we see 3 types of solution: general solution and a particular solution, and also a singular solution. And we can see further examples. So, another example, say example call it 3. So, consider a differential equation dy by dx is equal to y square minus 4, y square minus 4. Again, by the method of separation of variables, and you can integrate, and you can easily see that yx is equal to 2 plus 2 some constant c times e to the power 4x divided by 1 minus c e to the power 4x is a general solution. I leave this as an exercise to show that y is a general solution. And once you specialize, say when c is equal to 0, then we obtain y is equal to 2 is a particular solution. Now this can also be shown that observe that yx is equal to minus 2. If you look at the function, constant function yx is equal to minus 2 also satisfies the given differential equation. So y is equal to minus 2 is also a solution which cannot be obtained from the general solution. So therefore this y is equal to minus 2, this solution that cannot be obtained from the general solution. So hence, so therefore this is a singular solution, is a singular solution. Okay, now we look into initial value problem, where an initial value problem need not have a solution, or another initial value problem have more than one solution, or an initial value problem has a unique solution. These three situations. So initial value problem cases no solution, infinitely many solution, and unique solution. So these three situations. So we will look into some examples of initial value problems that has a unique solution and infinitely many solution and no solution, all these situations we will. So let us first consider a linear case. So later on we will give sufficient condition to ensure under what condition an initial value problem has a unique solution, and under what condition a solution has a solution and a solution is unique, and all such things we will deal with later. So example 4, just to get a feel of existence and non-existence of solutions, we take a few more examples. So consider the initial value problem, say dy by dx is equal to say 2 by x y with an initial condition y at 0 is 0. So obviously this is a linear equation. So linear differential equation, and is homogeneous, linear homogeneous, and variable coefficient. So, this coefficient is variable 2 by x. So, is a and there is no term which does not depend upon y. So, therefore, it is a homogeneous, and obviously it is linear with respect to the unknown function y. So, therefore, it is linear differential equation. Now, let us look into the solution again by the method of separation of variables. Method of separation of variables. We have dy by y is equal to 2 by x into dx, separating out the variables and integrating and adding a constant, call it C0. So, we can write this is a ln of y, this is 2 ln of x plus a constant C0. So, which is ln of y, which is ln of x square, 2 ln of x is ln of x square plus C0, and bring this term over here, ln of y minus ln of x square is equal to C0. Okay, that is ln of y by x square is equal to C0, or taking exponential on both sides, get y by x square is equal to e to the power C0. So, call this as C. So, therefore, y is equal to C into x square is the solution, is a general solution where C is a arbitrary parameter. Okay, for every value of C, y is equal to x square is a solution, and in order to satisfy the initial condition y at 0 is equal to 0 is obviously satisfied. Y at 0 is C into 0 square, which is 0 is obviously satisfied or for all values of C. So, therefore, y is equal to C x square is a solution to the initial value problem. It is satisfying the differential equation, at the same time it is also satisfying the initial condition for all values of C. So, y is equal to C x square is a solution to the initial value problem for every value of C. So, what does it say? It says that the initial value problem has infinitely many solutions. So, if you look at the solution, so this is a parabola, y is equal to C x square for one value of C, and for another value of C, this is another parabola, y is equal to C 1 x square, y is equal to C 2 x square, and for any value of C. So, this is also another solution. So, this is a family of parabolas. You get infinitely many parabolas happens to be solutions of the initial value problem. So, therefore, for an initial value problem, there is a possibility that the solution is not unique. It may have infinitely many solutions. Now, if you look at the same problem, the same equation with a different initial condition. So, look at the same problem. So, if the example is 5, then dy by dx is equal to 2 by x y. Now, the initial condition is changed, y at 0 is 1, and as we have already noticed that all solution of this initial value, this differential equation should pass through the origin. So, it cannot pass through the point 0 1. So, 0 1 is a point you are looking for. You want the solution to pass through the point 0 1, okay, when x is equal to 0, and this is not possible. So, there is no solution, this is 1 which is passing through the point 0 1 and is also a solution to this differential equation. So, no solution satisfies the initial condition. Y at 0 is equal to 1. Okay, why? Because y of x is c into x square, and you want y at 0 is equal to c into x is 1 0 square, and you want this to be 1, which is not possible. So, therefore, the moral of the story is no solution to the initial value problem. dy by dx is equal to 2 by x, y, the initial condition y at 0 is equal to 1. And one more thing we observe, that if we change the initial condition, okay, for the same problem, say example 6, the same differential equation dy by dx is equal to 2 by x y, and y at 1 is 2, say for example. I am giving a condition at 1 which is a non-zero condition, the value is non-zero. So, it can be shown easily that y of x, we have already seen the solution is of the form c x square, and you are looking for y at 1 is equal to c into 1 square, which you want this to be 2. So, this implies that c is equal to 2. So, therefore, y is equal to 2x square, y is equal to 2x square is a unique solution. So, this example, the same problem with a different initial condition dy by dx is equal to 2 by x into y with a different initial condition y at 1 is equal to 2 has a unique solution. So, same differential equation which is giving rise to 3 different situations where no solution, and where there is unique solution, and also there is infinitely many solutions. Now, we look into the solution of a differential equation where it is defined. So, our equation is dy by dx is equal to f of x y, initial conditions y at x 0 is y 0. The domain of in which the solution is defined. So, for a initial value problem of this form, there may be a solution starting from the point x0, x0, y0, and that solution may exist only for some interval on the x axis. So, this is x0 and this is y0, and this is a point from where we start x0, y0, looking for a solution, and the solution is yx, and it can in some many of the initial value problem this interval, okay, call it x1, the solution exists in a small interval x0, okay, x0, x1, okay, this is called the domain of solution, domain of solution y. And it can happen that the solution is defined on the entire x axis, and some problems it is defined only on some small interval or only on some particular bounded set in the x axis. So, for that also we look into some examples. So, example example 7. So, consider an initial value problem. So, consider an initial value problem given by dy by dx is equal to y square, and initial condition is y at 0 is equal to b, a positive number. Okay, this is a nonlinear differential equation. The initial condition is y at 0 is some number b. We are starting at this point 0 b, and we are looking for a solution y. So, from the point x is equal to 0. Okay, let us look at the solution again by the method of separation of variables. So, by the method of separation of variables, so we get separating out the variables, this is 1 by y square dy is equal to dx, and integrating, adding a constant c, and integral of 1 by y square is minus 1 by y is equal to x plus c. So, this just by simplifying you get y is equal to minus 1 by x plus c. So, the solution is y is equal to minus 1 by x plus c. Now, the initial condition y at 0 is b. So, this implies that y at 0 is equal to b, which is equal to minus 1 by c. So, this implies that c is equal to minus 1 by b. So, plugging this value to the solution, y of x is equal to minus 1 by x minus 1 by b, which is equal to b by 1 minus bx. So, this is the solution to the initial value problem. So, the solution is y of x is equal to b by 1 minus bx. So, look at the solution. So, starting from 0 b, as you increase x, if x is less than 1 by b, see if x is equal to 1 by b, then the solution blows up. So therefore, solution exists. So this exists for x strictly less than 1 by b. So therefore, if b is okay, the solution exists 1 by b. If b is 1, then 1 by b is 1. So this is 0 to 1. So for example, b is equal to 1, then solution exists. The domain of solution is 0 to 1. But if b is a very large number, so if b is large, so 1 by b is small, and hence the domain of existence is from 0 is very small interval. Okay, note that although the equation looks to be a very nice equation, the initial value problem looks nice on the entire real line. Starting from 0 b, the solution yx exists in a small interval 0 1 by b. So 0 1 by b, if b is large, is a small interval. So solution exists. If b is large, then the solution exists on a small domain to the right of x is equal to 0. Now, looking at another problem example, call it example 8. Here non-uniqueness non-uniqueness of nonlinear initial value problem. So consider the initial value problem. So given by dy by dx is equal to 3y to the power 2 by 3, and the initial condition is y at 0 is 0. So this is also a nonlinear differential equation with a given initial point 0 0, initial condition is 0 0. So you are looking for a solution that starts from 0 0. And again by the method of separation of variables, So this is dy 1 by 2 to the power 3 by 2, so 3 is equal to dx, and integrating and adding a constant c, so which is integral 1 by 3 y to the power minus 2 by 3 dy, which is equal to integral dx is x plus c. So integral of this one y to the power minus 2 by 3 plus 1 or divided by minus 2 by 3 plus 1, which is y to the power 1 by 3 is equal to x plus c. Or so this implies that the solution y satisfies the solution is given by y of x is equal to x plus c the whole cube. And now applying the initial condition. Applying the initial condition, y at 0 is 0, which implies that 0 plus 3 all cube. So, implying that c itself is 0. So, that means we get a solution yx is equal to x cube, okay, for the initial value problem. So, the solution looks like a function y is equal to x cube. So, this is a solution, and we can also see that. So, consider some other functions. So, consider the function for k is a positive constant yx defined by yx is equal to 0 for x is less than or equal to k and greater than or equal to 0, and x minus k the whole cube for x strictly greater than k. So, if you consider these functions for every value of k positive, this gives a family of functions yk. So, this for every k you have this function, and you can show that, or you call it is a yk, and obviously the derivative, if you differentiate it, the derivative of this one, so this looks like up to k, say this is k, up to k the value of the function is 0, from k the function is smooth. So, x minus k cube, and if you is a smooth function, if you differentiate it, y prime x, okay, is 0 for x between 0 and k, and its value is 3 times x minus k square for x greater than k. For a different k, so this is another k, let's call it k1, and another k. So, the value of the function up to k2 is 0, then it is x minus k2 cube, and you can see that the derivative y prime x satisfies, because of this form, this satisfies the given differential equation. This is 3 times y to the power 2 by 3. So, for all x greater than 0, and it satisfies y at 0 is 0. So, you can say this is okay, you can show that this is a family of curves. So, therefore, and also you can see that yx is equal to 0 is also a solution. So, y x is equal to 0, 0 function is also a solution which is a singular solution, otherwise you get a family of solution. The conclusion is the given initial value problem has infinitely many solutions. Okay, in this lecture what we have discussed is we have taken a few initial value problems and we posed the well-posedness of Hadamard and have seen that there are problems in which the initial value problem has no solution, and there are problems in which the initial value problem has a unique solution, and there are initial value problems having unique solution. And now how to characterize these solutions, these properties, that we will see in the next lecture. Okay, bye.